So most of the recent videos that we've done have focused on adding water in a Markovnikov sense via an addition that is fundamentally from the opposite side. So a Markovnikov addition of water in what we would consider an anti-sense. What I mean by that specifically is the product that you would expect from these reactions, either pure sulfuric acid plus water, or by doing mercury in the first step and then sodium borohydride reduction in the second step, is that you would end up forming this product right here. And I'm not specifying the stereochemistry because there is no stereochemistry, there's a plane of symmetry right there. And this is what I mean by the Markovnikov addition. In other words, this is going to go via either a explicit cation at the tertiary position to which the water adds, or alternatively, if the mercury adds first, you get the mercuration. You get the little triangle with the mercury having the plus charge on it, but then the water comes in, water as the solvent in that first step, comes in and adds at the tertiary position because that's where the area of greatest plus charge is. And that gives rise again to the Markovnikov product after you do the sodium borohydride reduction to make the mercury go away. If you're interested in exactly how that works, again, go visit the oxymercuration video. But though you can't see it here because of the fact that the mercury goes away, that's explicitly happening from opposite sides. The mercury, if it added from the one side, then the water would have to add from the opposite side, and that's because mercury is huge. And to illustrate that, what I have here is the bromine species, and again, what you're going to do is make the bromonium first, and then water is going to add, and water is going to add explicitly at the tertiary position. Again, you're going to have a tertiary and a secondary. Water adds at the tertiary position, but the water has to add from the opposite side that the bromine added first. So if the methyl ends up and the bromine ends up, then the water ended up attacking from the back. And that's what I mean by an anti-addition. We added a bromine and a water. Bromine ended up on one side, water ended up on the other. So all of this is set up for, surely there's a way to run an anti-Markovnikov addition. In other words, if the normal thing is to attach the incoming group at the more stable of the two possible carbocations, then there has to be a way to do it the opposite way, the anti-Markovnikov fashion. So what reagents do that? And likewise, if there's a mechanism that's fundamentally always from opposite sides, then surely there's a mechanism that's from the same side, SYN. And so what we're going to do is have a reagent that does both. There's going to be a reagent that adds water in an anti-Markovnikov fashion, and it will do so fundamentally as a SYN addition. The key reagent here is going to be borane, BH3. Often this reaction is run in THF as a solvent, and the result of this first step, which you typically don't isolate, is to put the boron at the anti-Markovnikov sense and put the hydrogen at the more congested internal position. So in other words, what you're going to do is you're going to put the boron, the new boron, at the terminal end, and you're going to put a hydrogen at the internal end. And again, you don't isolate this material, you do this as a two-step process, and the result of the two steps is to essentially add water at the end. So this is going to be your anti-Markovnikov fashion. Now, the substrate I've chosen here is not one that allows us to illustrate the SYN nature, but we'll get into that when we get to the mechanism. So the key feature of the reaction I'm about to show you as we walk through the mechanism is that you're going to end up adding the opposite sense of the water than we did before. And we're going to do so in a SYN manner rather than an anti-manner. Okay, so the reason why this video exists is because we need a tool to create a water addition across a double bond in a way that is opposite what will normally happen. So if you have a normal terminal double bond, monosubstituted terminal double bond, most of your ways of adding water across the double bond will put the water, the oxygen part, at the more stable carbocation, and that's known as the Markovnikov product. But if instead you use borane and then you work it up the right way, you end up adding water in such a way that the oxygen ends up at the terminal primary position, which is the anti-Markovnikov product. Specifically, that happens because we're doing a SYN addition that leads to an anti-Markovnikov sort of borane intermediate. You don't actually isolate this. In fact, you run this reaction, that's the step one, you just throw in borane, usually in the presence of THF. It does the addition you want to make the anti-Markovnikov product. You then take that same exact flask, so the same physical flask, and you throw into it hydrogen peroxide, sodium hydroxide, and extra water, and what that does, through some some magic that I'm not really going to explain, but will describe a little bit, make the boron-carbon bond break and replace it with a carbon-oxygen bond. And again, the overall result of that two-step sequence is addition of water across the double bond in an anti-Markovnikov fashion. And this is a very useful tool. If we can add it the one way, you want to be able to achieve the other regiochemical outcome, and this is the tool that allows you to do that. So put this tool in your toolbox. If you need to add water, anti-Markovnikov, Borane in THF is the first step. A oxidative workup, hydrogen peroxide, sodium hydroxide, and water is the second step, and the result is from there to there, boom. That's the tool. How does it work? For that, what I want you to remember is that borane itself is a molecule that both desperately wants to pick up an extra pair of electrons because it lacks an octet, so it really needs a pair of electrons. But as soon as it picks up that extra pair of electrons, it instantly has too much electron density and wants to act as a nucleophile. So in other words, what you have is an empty orbital that needs to be filled, and as soon as you fill it, then you have too much electron density and you want to get rid of that electron density. So that combination of factors lines up perfectly when you have a nucleophile right here, a double bond, and you have the empty orbital in close proximity. The electrons from the double bond are going to go fill that orbital, and as they do that, you're putting a minus charge on the boron, which it really doesn't want to have, but at the same time you're putting a minus charge on the boron, you're putting a plus onto the carbon, which it doesn't want to have. And the combination says that then this boron-hydrogen bond is going to slide over and make a bond and become a carbon-hydrogen bond instead. This is a one-way reaction, all downhill. And the upshot from this first step is that the boron-hydrogen bond has now added and become that one, and the primary carbon has made a bond to the boron and created that. And so if I were to draw in the other hydrogens here, there were two hydrogens at this position. Those two hydrogens are now located there. This was the new hydrogen that added, but there was a hydrogen there to begin with. So now we have two hydrogens at this position. So this is what we have formed in the first step. Now, why does it work the way it does? Well, because boron is relatively larger than the hydrogen. So you're going to align the boron with the carbon on the end as opposed to the carbon that has more stuff, the R group. So you're going to put the boron out here where it is away from the R group, and you're going to put the hydrogen closer to the R group. In other words, what's organizing this transition state is size, or perhaps STERICS. In other words, the reason why you get Markovnikov addition is because you have a carbocation. So if we want to do anti-Markovnikov addition, we have to avoid carbocations altogether. And so this happens simultaneously, and the hydrogen is delivered from the same side that the boron is on. They end up in the same side because this happens again all at the same time. So it's organized the way it is regiochemically because of size, because of STERICS, and that leads to the anti-Markovnikov product. But there is something I want to point out here, and that is that the product of this first addition is a boron, still, with an empty orbital on it, and now two hydrogens. In other words, this material right here could react again. In other words, one of these hydrogens could now be a boron with an R group on it. And now you're going to do the exact same reaction again. And what that'll do is now have two of these chains with R groups on them. Okay, now this material still has an empty orbital, and what that means is it could plug back in right here, and now we have a material with two R groups on it, and it does one more reaction. And once that reaction is done, now what we have over here is that material like so. So the key point is that this starts off as relatively unselective because it was borane with just three hydrogens on it. It was relatively small. But as the reaction proceeds and you use the same boron potentially 3 times to react with the double bonds, it gets bigger and bigger and bigger. So your selectivity actually gets better as the reaction progresses. Again, every time what you're doing is delivering a BH bond and it's organizing on the basis of size. But after you've delivered the first, then you now have a longer R group and you can add another R group and so on. However, if selectivity is really important to you, then there are in fact reagents that would allow you to do this in the first place. And one of them gets abbreviated more or less like this, and it's called 9BBN. And this boron you can only use once in your reaction, and it's relatively more expensive than borane, but it has the advantage of having a relatively large group out there in the first place, so it's selective right from the jump, because you have this large group that's taking up all space and organizing the transition state the way you want. Whether you choose to do it this way, whether you choose to do it this way, whether you choose to use other reagents that we will encounter later in the course, it doesn't matter. The overall message is the same. You're going to organize on the basis of size instead of a carbocation, no carbocations are formed because this happens all at the same time. Because it's happening all at the same time, the hydrogen and the boron are added from the same side of the double bond. Therefore, it's a SYN addition. None of this intermediate stuff matters because then we're going to run some magic to remove the boron and replace it with an alcohol. So the overall addition is an anti-Markovnikov addition of water across a double bond. This is just a tool in your toolbox for achieving that if you want to add water, but not the regiochemical outcome you get when you simply use acid plus water or mercury plus water.